It's time to fire up Germany's revolutionary fusion machine. It's a tense moment.
SPARC has the potential to transform our energy system entirely, leading us towards a future powered by endless clean fusion energy. This groundbreaking project aligns perfectly with our desperate need for sustainable and efficient energy sources, aiming to power everything from our homes to entire cities without damaging the planet. What if SPARC changes the energy game within this decade? Join us as we uncover what this groundbreaking technology might achieve to benefit our dying planet. Overcoming fusion's greatest challenges. The development of SPARC is a complex process involving advanced materials and cutting-edge engineering. Each step brings its own set of hurdles, but the potential rewards are enormous. If successful, SPARC could lead to a future where fusion energy is a key part of our energy mix. The development of these HTS magnets for SPARC was a major shift from the usual superconducting magnet technology. A unique feature of this new design is that the superconducting tape has no insulation. At first, many people were skeptical about this no insulation approach. However, it turned out to be a success, leading to better stability and performance of the magnets. By removing the insulation, engineers made the manufacturing process simpler, reduced the risk of electrical problems, and improved the efficiency of the cooling system. The success of these new magnets shows that sometimes taking a bold and unconventional approach can lead to groundbreaking advancements. But there's more to this story. The journey to creating these HTS magnets was filled with trials and errors. Despite the initial doubts and setbacks, the team's persistence paid off, leading to innovations that could revolutionize the field of fusion energy. This achievement is a testament to the power of innovative thinking and determination. These new ideas went through a tough and detailed testing process. The magnets were pushed to their limits in many situations. This was to make sure they could handle the stress they would face in real use. The good results from these tests showed that the new magnet technology is practical and strong, making it ready to be used in SPARC. This success is a crucial step toward building bigger and better fusion reactors that can run continuously and produce electricity. This development is essential for the future of energy. It aims to offer a cleaner, sustainable alternative to the fossil fuels we use today. Yet achieving continuous operation is still a significant hurdle to overcome. The results from SPARC are very important for the future of RC, which will be the first fusion power plant built with this new technology. Learning from SPARC, ARC aims to produce 200 megawatts of electricity. This big step forward makes fusion energy a strong option for everyday use. While the big ITER project in France works on fusion in a large and complex way, SPARC takes a different approach by focusing on a smaller and cheaper method. Its compact design and advanced technology aim to make the fusion process simpler, cutting both costs and time needed for development. This approach not only supports the work at ITER, but also speeds up the goal of making fusion energy a regular power source. But wait, there's more. A new twist in the SPARC's journey promises even bigger breakthroughs in fusion energy. SPARC and ARC's revolutionary impact. SPARC's innovative strategy could mean faster progress toward affordable and reliable fusion energy for everyone. And that's just the beginning. All right, let's talk about these cool science projects called SPARC and ARC, where smart folks at MIT and a company named Commonwealth Fusion Systems are working together to make a new kind of energy that could change everything. So SPARC and ARC are all about fusion energy. Think about the sun and how it powers itself. It's like that, but here on Earth, fusion could give us tons of clean energy without running out. These projects use some super advanced magnets that can handle extreme conditions needed to make fusion happen right here. These new magnets they're using are pretty wild. They can create a super strong magnetic field in a smaller space than ever before. This means the machines needed for fusion can be smaller and more powerful. This is a game changer because it makes building these machines a lot easier and cheaper. But this wasn't the easiest thing to figure out. They had to start from scratch with how they made these magnets. The material they use now is way different from the old stuff. It's called Rebco, and it's much better at conducting electricity and handling the high temperatures needed for fusion. They even got rid of some parts that were usually necessary, like insulation. Normally magnets have this to stop short circuits, but with the new material, they didn't need it. That was a big risk, but it paid off because it made the magnets simpler and more robust. Now imagine a machine that's not just a big donut of metal, but a powerhouse that can harness the power of stars. That's what SPARC is trying to do. And once they get it right, ARC will take over and start turning this into a real power source we can use. It could mean a lot less reliance on stuff like coal and oil, which is great for the planet. Yet the road wasn't smooth. When they first tested these new designs, they really pushed them to see what they could handle. They even intentionally caused what's called a quench, a big no-no usually because it can wreck the magnet. But they needed to see if their new design could handle it, and guess what? It did. This breakthrough has a lot of people excited. It means that these smaller, more powerful fusion machines could be built faster and start changing how we get our energy sooner than we thought. While SPARC is still under development, aiming to show it can produce more energy than it uses, ARC is already on the drawing board to scale things up. They're planning for ARC to be the first of its kind, a fusion power plant that's not just a science experiment, but something that could actually power cities. It's a big deal because it combines decades of research with these new tech advances. The folks at MIT and CFS aren't just making a new type of energy, they're working to make it practical and ready for the real world. And that's something that could really make a difference for all of us, giving us a cleaner, more sustainable future. Yet, the real game changer is the potential to revolutionize the energy industry. Imagine a world where we no longer rely on fossil fuels or face the limitations of renewable sources like solar and wind. Fusion energy could provide a stable and continuous power supply, transforming how we live and work. The success of SPARC and ARC could lead to a future where energy is not only cleaner, but also more accessible to everyone around the world. This would mark a significant shift in how we think about and use energy. The partnership between MIT and CFS is a key factor in the rapid progress of the SPARC project. This collaboration combines MIT's vast experience in fusion research with the innovative and well-funded efforts of the startup CFS. Together, they are working towards bringing fusion energy to the world within the next 10 years. The goal is to make a big impact on global energy by offering a cleaner, sustainable alternative. This journey, MIT and CFS are setting new standards. Their work is inspiring, showing that with the right partnerships and dedication, we can solve some of the world's biggest problems. But this wasn't the only impressive part. Their success could pave the way for more collaborations like this, where academic knowledge and startup agility come together to create groundbreaking solutions. It's a powerful example of how working together can lead to amazing results, bringing us closer to a sustainable and clean energy future. Now, let's dive into why we urgently need new sustainable energy solutions. Powering tomorrow with stellar energy, progress Most of the world's energy still comes from burning fossil fuels, making up over 80% of our global energy supply. This practice severely harms our environment with CO2 and other pollutants. Climate scientists have been warning us about the dangers of climate change, like rising sea levels affecting coastal areas and more extreme weather events. These problems show we need to act now. While it's too late to undo some damage, we can still reduce further harm. Pablo shared data on US electricity generation trends from 2010 to 2020 and projections up to 2050 from the Energy Information Administration. Even with a rise in renewable energy sources like wind and solar, fossil fuels are expected to make up half of our energy production by 2050. This shows how crucial it is to change our energy system. The future of energy, according to Pablo, must be free from greenhouse gas emissions, scalable, safe, and sustainable in the long run. The perfect energy source should fit easily into our current power grids without needing major changes. Looking ahead, developing these technologies is not just a good idea, but essential for a sustainable future. At the MIT Plasma Science and Fusion Center, we are dedicated to finding out how fusion energy can help meet our energy needs. Fusion is often confused with nuclear fission, but they are different. The nuclear in nuclear fusion refers to processes involving the atom's nucleus. In nuclear physics, there's a graph that shows the average binding energy per nucleon against the mass number of elements. While you don't need to understand binding energy, it's important to know that higher values on this graph mean greater nuclear stability. Where the protons and neutrons are more stable, nuclear fission, elements like uranium are split to form lighter elements, moving them to a higher stability point and releasing energy. In fusion, we combine light elements like hydrogen isotopes to form heavier elements. This process also releases energy, but through combining nuclei instead of splitting them. The challenge with fusion is that atomic nuclei are positively charged and repel each other. How can we make these repelling nuclei come together to fuse? One way is to accelerate the nuclei to high speeds, allowing them to collide and overcome their electrical repulsion. When they get close enough, the strong nuclear force, which is attractive, takes over and allows the nuclei to fuse, releasing a lot of energy. Achieving fusion requires extremely high temperatures, initially thought to be around 3 billion degrees. This poses a big challenge. How do we reach and maintain these temperatures and contain the hot plasma formed? But here's an interesting fact. By considering quantum physics and the phenomenon of quantum tunneling, we find that the required temperature could be lower, around 150 million degrees Celsius. Still, this is very high. Here's a challenge. How do we handle the extreme conditions needed for fusion? The magnetic danger of plasma. You might be wondering if these extreme temperatures make fusion impractical in such a hot plasma on Earth. What materials could handle these conditions? This is where magnetic fusion comes in. When hydrogen is heated to 100 million degrees, it turns into plasma, a soup of charged particles. Plasma, the fourth state of matter, behaves differently from solids, liquids, or gases. In plasma, atoms break down into a cloud of electrons and nuclei, interacting as charged particles. When particles get charged, they react to electric and magnetic fields. This is really useful because, by creating a magnetic field, we can control these high-energy particles. By carefully manipulating them, we can keep these particles away from the reactor's walls. The key is to shape the magnetic field into a continuous loop, which effectively seals off any ends. This creates a donut-shaped chamber where the plasma stays contained and the particles continue their controlled movement around this loop. The device that makes this possible is called a tokamak, a special type of fusion machine. One of its main parts is the toroidal field coil. These large components, usually between 16 to 18, surround the machine. They create a magnetic field that wraps around the device in a circular direction. But here's the problem. A purely circular magnetic field isn't enough to keep the particles confined forever. Over time, particles would drift and hit the tokamak's walls. To stop this, another magnetic field, called the poloidal field, is added. This field goes along a different axis. Tokamaks create this poloidal magnetic field with a central solenoid located in the middle of the machine. This solenoid works like a transformer, inducing an electric current in the plasma that moves in the circular direction. This current naturally creates a poloidal magnetic field, keeping the plasma stable and contained. The combined magnetic fields in the plasma form a helical shape, effectively keeping the particles centered and controlled within the machine. This level of control has been refined over many years with experience from tokamaks around the world. The International Atomic Energy Agency has a detailed database listing about 55 active tokamaks globally, with a total of 170 built over time. But this isn't the worst part. A natural question is whether these machines can achieve fusion. The answer is yes. Fusion reactions happen regularly within these devices, and byproducts like neutrons are measured daily. However, there's still a big challenge. The energy needed to heat the plasma to a staggering 100 million degrees is still more than the energy produced by fusion. The fusion community uses a metric called fusion gain, or Q, which compares the power output from fusion to the power input needed. The highest Q achieved was 0.6 by the Jet tokamak in the UK in the 1990s. However, the break-even point, a Q of 1 or higher, where the energy output matches or exceeds the input, has not yet been reached. This is a crucial goal for fusion to be a viable energy source. To be truly effective, the fusion ratio needs to be greater than 1, accounting for system inefficiencies and aiming to produce excess energy. Although significant progress has been made, reaching this point remains a key objective in fusion research, symbolizing the balance between energy consumed and energy generated. And finally, researchers are exploring two key ways to make fusion more efficient, pushing the boundaries of plasma physics. The first involves building larger machines, specifically by increasing the size of the torus in devices called tokamaks. These machines are crucial for holding and controlling the high-energy plasma needed for fusion. The second path focuses on making the magnetic fields inside these machines stronger. Over the next few minutes, we will dive into why these two factors, size and magnetic field strength, are so important for improving tokamaks' efficiency. First, let's look at the basics of nuclear physics, which gives us a key formula to calculate the power output of fusion reactions. This formula shows that the total power, measured in watts, depends on the density of the fusion fuel, deuterium and tritium, two types of hydrogen, how often these particles collide, the energy released per reaction, and the volume of plasma where these reactions happen. Next, we shift our focus to plasma physics. Here, we study how reaction rates change with temperature using a unit called the kiloelectron volt, keV, where 1 keV equals an incredible 11 million degrees. Among these reactions, the deuterium-tritium reaction is the most common and powerful, making it the top choice for tokamak fusion. The temperature range of 100 to 200 million degrees, the reaction rate coefficient increases with the square of the temperature. This relationship makes our calculations simpler and lets us focus on the key factors that affect fusion efficiency. With an equal mix of deuterium and tritium, we find that the fusion power per unit volume is directly linked to the square of the plasma pressure, a crucial measure of fusion performance. But increasing plasma pressure endlessly isn't possible. Experiments have shown that there's a limit to how much pressure a tokamak can handle. This limit is described using a ratio called the normalized pressure, which compares thermal pressure to magnetic pressure. This ratio depends on key tokamak parameters like electric current and the minor radius of the torus, multiplied by the magnetic field strength. The maximum pressure that can be sustained rises linearly with these parameters. Beyond this point, the plasma becomes unstable, and the tokamak can't operate. This leads us to adjust our fusion power equation, adding a factor known as the normalized beta, which must stay below a certain level to ensure stability. By understanding and optimizing these factors, researchers keep pushing the boundaries of what's possible in fusion technology. They aim to achieve higher pressures and better containment methods within the structured chaos of a tokamak. This ongoing scientific effort not only deepens our understanding of fusion, but also brings us closer to harnessing this clean, almost endless source of energy. But remember, this isn't the end of the challenges. Will fusion energy ever truly become our primary power source? Or is it an unattainable dream? Share your thoughts in the comments, like and subscribe for more.